In this video, I'm going to demonstrate where the quadratic formula came from a normal quadratic function, a generic quadratic function, ax squared plus bx plus c. So a, b, and c can be anything, right? Any real number, let's say that. Now, you should know the quadratic formula by this point. Okay, we're reviewing actually where it came from. There are many versions of how to memorize it, like based on songs, stories, or just plain old rote memorization, but I put that in green right above. That way we know our goal, right? That's what we're shooting for. At the same time, I'm going to use this technique to solve an actual problem because sometimes with so many letters, right, like we get lost in translation. What are we supposed to do? So the example over here, we could just use the quadratic formula, right? Plug 3 in for A, -4 in for B, -5 in for C. But I'm going to use this process of deriving the quadratic formula with that. So we're actually going to complete the square because that's how the quadratic formula is derived. So I should add by, I'm just going to put CTS, by completing the square. All right, so completing the square with an A term, it gets a little ugly. So I'm actually going to start with the example and then move to the left of the generic. What we do first is we get rid of this C term. So I need to add the 5 on both sides, right? That way we have 3x squared minus 4x. I'm going to leave a little bit of room there, equals 5, and you'll see why in a minute. So on the left side, using that same technique, I have a plus c, so I would do the opposite, right? We're going to subtract c. So we have ax squared plus bx equals -c. So our goal was to remove the constant term. I'm going to kind of keep notes as we go. So isolate, really what we're doing is we're isolating the variables, right? We're getting all the x's on one side and all the constants on the other. Okay, step 2. We need to remove the a term. How we do that is by factoring. So I'm going to remove this a term and we're going to factor. So 3 times x squared, right? I factored a 3 out. Well, the b term gets a little weird here, but if I had a -4, the easiest way to do that, if I factored out a 3, is to divide by 3, right? So why is that? Well, double check by distributing. This would be 3x squared. We're good there. -4 over 3 multiplied by 3 is -4. And then, of course, we have the variable x. So we're good there. All right. Again, I'm going to leave kind of a blank spot there. I do nothing on the right-hand side. So my goal, again, is to factor out a. So over here, we have a. Similar reasoning, if I factored out a, I'd have b over a x. Okay, again, you could check with distribution. A multiplied by b over a x would just be bx. All right, now we need to complete the square. Completing the square is a two-step process. How I like to do it is I do half of the b term and then I also square that, but really the half the b term goes down to the next line. So let me demonstrate with the real numbers over here first. So b is -4 over 3, right? So let's do this scratch work off to the side. I need to half -4 over 3. Let's move this over just a little. And that is negative, well, I could reduce the 2 and the 4, but about -2/3. Right, we just reduce those terms. And now we take negative 2/3 squared, and that's 4/9. I need both of these numbers, and that's why I wrote them off to the side. So the squared term, actually the end of our scratch work over here, is what we need to add and subtract. So in here, let's go and use green. I need to add 4/9 and I need to subtract 4/9. We're allowed to do that because that's 0, right? Really, I added 0. You could add 0 to any problem and you still get 0. The half, though, where that comes into play is when I go to factor this next line, the negative 2/3 is going to be my perfect square. When we complete the square, that term will, by design, and that's a topic for another video, but by design, completing the square yields us this. Okay, now we have more work to do there, but let's check that out on the left-hand side. Two-step process, right? We needed to do half of b. So in this case, the b term is b over a. So half of b over a is b over 2a. By the way, you'll start noticing some of these come up over here, right? There's the b over 2a. Anyways. And then we need to square this. So again, this is my scratch work. B over 2a squared is b squared over 4a squared. All right. I'm gonna go ahead and move this down a line. I need a little more room there. Okay, so we're going to add and subtract that b squared over 4a squared. And remember the next line, we have the perfect square. Okay, and then we'll leave that for now, and we'll check out what else happened. Okay. Well, by design in completing the square, this 4 over 9 here was needed. Okay, all of this stuff here created this perfect square, and we still had a 3 outside. But this negative 4 over 9 was not part of that. So if we distributed and collected like terms, I'd have 3 times negative 4 over 9, right? 3 times negative 4 over 9. So I just wrote negative 3 instead, but that's the same, right? 3 times 4 over 9 with a negative. So I have this term still. If I distributed everything and I factored, I'm a factoring genius with fractions, right? I would have this for all of that. But then this last piece with the 3 is here, right? So using that concept over here, I would still have my a, right? And you distribute times b squared over 4a squared. And it's negative again because of the negative there. Alrighty. Oops, equals 5 on this side. Okay, so that was the whole completing the square. Now our goal is to solve for x. So we need to isolate x again. We began by isolating the x's, but then we had to complete the square because we had 2 x's, right? I need only 1. So my goal again here is to isolate that x. So that's the goal on this side, is on the right hand side as well. So the first thing we would need to do is add this stuff we did in green to the other side. Let's go ahead and simplify it first. So, right, the negative 3 times 4 over 9 would be negative 4/3. So I'm going to add 4/3 to both sides. So we have 3x minus 2/3 squared equals 5 plus 4/3. So, of course, we need an LCD. Alrighty. And that would be 19/3, right? 15 plus 4 is 19/3. All right. On the left-hand side, we have an a that would cancel. So I need to add b squared over 4a on both sides of the equal sign. And then let's write what we're left with. A times x minus b over 2a squared equals negative c plus b squared over 4a. Again, just like we did on the right, I need a LCD to combine the negative c plus b squared over 4a. So I need to multiply by 4a over 4a. Okay. Again, we're isolating the x. So the first thing we had to do is add the constants. Oops. Well, next we're going to have to get rid of that coefficient, right? We have to divide by a or multiply by 1 over a. So get rid of the coefficient. So on the right-hand side, why I say let's multiply by 1/3 rather than dividing by 3s, because that would, right, when we have fractions, it's just easier to do this rather than dividing by 3. But dividing by 3 and multiplying by 1/3 is the same result. So let's look at what happens next. We have 19 over 9. All right. On the right-hand side, same thing. We need to multiply by 1 over a. Negative 4ac plus b squared all over 4a. Okay, multiplied by the 1 over a. I'm going to scroll down a little bit, give us some room. Well, next we need to take the square root of both sides, because I'm left with this over here, right? I'm going to rearrange these only because you should notice this, right, is starting to look like the quadratic formula. So I'm going to do it in that order. Okay. Now, when you take a square root, you always need plus minus, right? Because we don't know. For instance, if I had x squared equals 4, just simplify it. I don't know if x is plus or minus 2, right? It could be a 2, but it also could be negative 2. So always remember plus minus. All right, so what did we do? We did the square root on both sides. The right-hand side looks like this. Now, the denominator notices a perfect square. Square root 19. So I'm going to simplify that to 3. We could take the square root of the numerator, square root of the denominator. Same thing on the left. X minus b over 2a equals plus minus square root b squared minus 4ac all over, right? 4a squared has a perfect square root of 2a. That is almost quadratic formula. We're so close. So last step, we did the square root. We remembered the plus minus, right? Last step is just add that b over 2a. So again, we're just add or subtract whatever other constants you have to isolate your x. right? We're trying to get x by itself. So here, add 2/3. Here, we need to add b over 2a. And we are done because just looked at the left-hand side. We already have an LCD, right? 2a. So I'm going to bring the b up front only because that's the way the quadratic formula looks. And on the right-hand side, it's more common to see it like this, right? But some people prefer to just leave it like this. I would say anytime there's an LCD, right, combine them. Pause, rewatch, rewind, fast forward, whatever you need on this video. I will say, the left-hand side, it's like, ooh, that is quite hideous with all those variables. But I will also point out, this is an Algebra 1 standard. Okay, my opinion, I think it's a bit beyond Algebra 1, maybe Algebra 2. But, even though we do use the quadratic formula and we do complete the square in Algebra 1 and Algebra 2, now in college algebra, usually we resort to the quadratic formula, but understanding where it came from helps you see, honestly, it wasn't like some crazy rocket scientist coming up with this formula. It was a simplified version of completing the square where we don't want to do that every single time, in my opinion. I mean, some people prefer that method. I want to use quadratic formula. There's where it came from. Hope that helps.